Okay, in case you want to correct numbers 3 and 5 as part of your rainy day points, some of you came up with a mathematical relationship using your XBreg button on your TI. Which is fantastic, totally fantastic. I wasn't expecting you to do that. I was just simply expecting you to realize there was a multiplicative relationship between one and the other. So if you went from one data point down, I was expecting you to see there was a common multiple or a common division. But a bunch of you, most of you I think, did it as far as number 2, you came up with the relationship y, I think it was 2 times 1.3 to the x. I think that was number 2.
Yeah.
So, and I think at number 4, you came up with y equals, I forget what the multiplier was, but 0.9 to the x?
0.9.
Yes.
And was there a coefficient?
2.
It was 2 again, okay. So I want to look at each of these in turn so you can understand how to answer 3 and 5. Because this was the one, of all the questions, these were the ones that kind of, I think, threw people for the most.
The
No.
number's off too, by the way. I would say 3 and 5.
No, but you guys came up with the equations into, well, okay, so the question is decay or increase, growth versus decay. In number 3, I asked by what percentage is the data either increasing or decreasing. So those of you that did it via the equational way, and we'll throw up on the screen the actual data, and I'll show you the numerical interplay in a second. It looks like most of you did it this way, though. When you look at, forget the 2. The 2 has nothing to do with the growth or decay. The growth and decay is happening in here. So the way we looked at this in class, the 1.3 to the x, the way we looked at that in class, and I've forgotten now exactly what growth model, I think it was the United States population, I believe. But you look at it as 1 plus 0.3 to the x. What does the 1 stand for? The 100% that remains each time. So what's the 0.3 stand for?
The rate.
The rate. What is 0.3 as a percentage? 30%. That's what the 0.3 stood for. The 0.3 is 30% increase. That's all I was looking for. A 30% increase. That's all I was looking for. You take whatever there was originally and add 30% to it. So that's the definition of exponential growth, is you're adding a set percentage each time, a percentage of what came before it. So that's all. That's all. I didn't expect it to trick people up, and I apologize. I apologize if it did. But if you had the equation like you did right then, the 1.3 to the x, the 0.3 jumps out at you. It jumps out at you. Now, the one that was a little bit trickier, I think, maybe, if you did it this way, and I wasn't expecting you to do it this way, I wasn't expecting you to do it this way, is this guy right here, the 2 times 0.09 to the x at number 4. So looking at number 4, that 0.09 to the x, and I remember doing this, I think it was the pond filter one that we did in class that one day, or it was the pond filter, or maybe it was the coin flipping. I forget which data set we were looking at when we did this in class together. But the idea here is that it's 1 minus 0.1 to the x. So 0.9 is 1 minus 0.1. Now, why would I write it as 1 minus 0.1? The 100% is the 1, and what are you losing each time? 10%. That was the answer to that one, is that it's a 10% decrease each time. It's a 10% decrease each time. A lot of you are saying it's 0.9. It's not tricky at all. It's actually extraordinarily straightforward. I mean, I was trying not to be tricky. This is why I asked the question like this. Give me 5 points. And you guys didn't agree with that. So the 0.9 is the amount left behind. You're leaving behind 90%, which means you're removing 10% each time. And we spoke of this with the filter on the pond, because the multiplier was 0.7, meaning you're leaving 70% behind each time, which means you're removing 30% each time. So I think that's just a fundamental misunderstanding of what a percentage to a decimal is. But you know what? That doesn't surprise me. It doesn't surprise me. It's one of those things that gets downplayed in algebra classes, and it's extraordinarily easy to kind of forget or to let slide. It's one of those things. Now, I did not expect you to do it this way. Honestly, I didn't.
Why not?
Well, because there's a much more straightforward way than running the regressions. And it's just looking at the differences in the data. It's going from one data point to the next. So when you go from, for example, in the first one, 2.6 to 3.38, let's see what I'm talking about up here on the overhead here, Lynn.
Yeah, but I mean, that's what we've been doing, Sean, is running.
We did it both ways, and you guys seem to like the other way better. I'm going by what I remember from class. And if you watch the videos, you'll realize that this is what you guys liked better. It was more direct. It was more of a direct definition, if you will, of exponential growth. I compared and contrasted it to quadratic growth, and you guys seem to kind of like it this way better. So, looking at,
I wrote it right, but I didn't write
there we go.
Oh, no.
Okay, so let's do this, clear. So looking, let me grab an in-class exam real quick. Get some numbers. Here they are. So looking at them, the first y value is 2.6. The next y value, this is 1a, is 3.38. If you divide 3.38 by 2.6, you get 1.3. If you take the next y value, 4.394, and divide it by 3.38, you get 1.3. And if you take any sequential y value and divide it by the previous one, you'll get 1.3. Now, the reason this is easier is because I told you that they're exponential data. So all you'd have to do is divide the second one by the first one, and then you'd know right there whether it was growth or decay, and what the rate was. That's why it's easier. You wouldn't. So many of you were saying, "I'm getting stuck on my TI. I'm getting stuck on the." That's fine, but you didn't need to do it that way. And then you'd also know what the value, the fifth value down would have to be once you do the expressions rate. Same thing with the last one. 1.62 from 1.8 is 0.9. 1.458 from 1.62 is 0.9. And I use these horrific looking numbers intentionally. I mean, they look awful, but the reason they look awful, they're picking up a decimal each time, is because I wanted them to be exactly those numbers. I wanted them to be exactly exponential, without any ish. In your homework questions, I had you guys dealing with the ish values. I didn't want you dealing with that on the exam. It freaks you guys out. At least the in-class exams. I like the out-of-class exams. The out-of-class exams are a little bit more, this is actually yours. So anyway, that's what I was after there. That's what I was after there as far as that goes. So at least you have, again, looking back to it, making sure you understand what those 0.3s and 0.9s actually mean. And I think a lot of it is just the fact that so much of percentages and fractions and knowing if zero is even, it's just one of those things that gets lost in your algebra work as you go through algebra classes when you're in pre-calc sequences. So, yeah. Other than that, the exam was fine. You guys nailed the probability questions. That was great. Other than a couple of them, I think, misread the math, but that's okay. Oh, which reminds me, I need to make sure that map is available for you guys for the corrections. Let me shut this down for a second. Leave myself.